we're going to look at the kind of numbers involved with how big things are. That's in terms of their physical size in meters, and also the mass in kilograms and the densities in kilograms per meter cubed. And then I think it's probably going to push on to Wednesday's lesson that we're going to have a look at the forces involved that are binding the nucleus together. So let's make a start today with size. Okay, so I want you to do a calculation. So you're going to need to have a piece of paper and a calculator in front of you. It's possible to calculate the size of an atom using reasonably everyday numbers. So these are all measurable things that chemists can measure with relative ease. So the density of copper is 8.96 grams for every centimeter cubed. And that's something you can do just by getting a lump of copper and putting it on a top pound balance and measuring it with a ruler. So that's a completely measurable number. Now there's a word from your GCSE past, the molar mass. So we'll come on to moles later on today, but to remind you, the molar mass of copper is 63.5 grams, which means that if you have 1 mole of copper, it will have a mass of 63.5 grams. Now that kind of means that you need to remember what a mole is. So for our current usage this morning, what you need to remember is that a mole is 6 times 10 to the 23 atoms. And again, we'll come on to that in a minute. So I'm going to stop talking for a minute, and I would like you to have a think about how could you use any of those numbers, well, you'll need all 3 of them, to work out D in the picture. How big is an atom? So I'm just going to be quiet and you have a little think about how you can do that. Okay, how are we doing? So I was just taking a quick register while you were doing that. So just again, let me know if your screen isn't working, if you can't see the screen again. Okay, so let's have a little look at what the answer is. Hopefully you've got at least part of the calculation, maybe even a final number. So this is the kind of calculation that we would expect you to be able to leap into at a kind of full A-level level. So here we go. You've been told that 1 cubic centimeter of copper has a certain mass in grams. We just always deal in kilograms and meter cubes. So we just need to scale that up from 1 centimeter cubed to 1 meter cubed. So there are 100 centimeters in a meter, and therefore there are 100 cubed centimeters in a meter cubed. So you need to multiply the number that I just gave you, which was this one. You need to scale that up by 10 to the 6. So 10 to the 3 of them are in this kilograms, and the other 10 to the 3 are there. So if I were to give you 1 meter cubed of copper, that's what its mass would be. Excuse me. And then you've been told how much a single mole, what the mass of a single mole is. So 63.5 grams for a single mole. So if you divide that number by 63.5 grams, you will get how many moles there are in a meter cubed. So there are just over 10 to the 5 moles in 1 meter cubed. And then I also told you that there are that many atoms in each mole. So if you multiply this number by Avogadro's number, that huge number, you'll get that there are 8.5 times 10 to the 28 atoms in a meter cubed. And now we just need to say, well, if there are that many atoms in 1 meter cubed, then how much space must they be taking up? Well, if the volume of each atom is taken to be a cube, now I know that an atom is a sphere, but it takes up the space of a cube because they pack in a cube-like manner rather than a sphere-like manner. There are gaps where the sphere isn't, but it's no other atom can be there. So the volume occupied by a single atom will be d cubed. So if you multiply the volume of a single atom by how many atoms there are, that needs to add up to 1 meter cubed. So if you divide 1 meter by this huge number here, that'll tell you what d cubed is. And then if you hit the cube root button on your calculator, you will get the diameter of a single atom. And that's fairly impressive, given that you can work out how big an atom is just by just from the density of the copper, which is a macroscopic variable that is easily measured. Okay, so just as an aside, note that this is 10 to the minus 10 of a meter, and that is a number that I would really love if you could keep in your head for the rest of the course. If you could remember that the diameter of an atom is in the region of 10 to the minus 10 of a meter, and that would be really helpful in common sense checks of the answers that you're going to be doing during the rest of this topic. Just as an aside, 10 to the minus 10 of a meter historically is often referred to as an angstrom, which you may brush across, you might have heard of before. It's named after a Swedish physicist from a couple of hundred years ago. And its letter is a capital A with a little accent on top of it. However, it's not an SI unit, and we won't be using it in physics. It's just in case you brush against it. 1 angstrom. Okay, so that is the diameter of an atom, 10 to the minus 10 of a meter, but what does that even mean? How can you even put that into a context? So here's some ways of thinking about 10 to the minus 10. So a human hair is about 1/10 of a millimeter, that's 10 to the minus 4, which means that you can fit 1 million atoms across the width of a single strand of hair. So if you just look at a piece of your hair right now, or feel a piece of your hair right now, that's 1 million atoms between your fingers, which is fairly impressive, but again, a little bit difficult to imagine 1 million atoms between your fingers. So if we scale it the other way and pretend that you are the small thing, how much bigger than you is something that's 10 to the plus 10 meters? And it turns out that that's roughly the radius of Pluto's orbit. And so you are as small compared to the entire orbit of Pluto as an atom is small compared to you, which puts it into context a little bit better for me. Atoms are really, really very small. Don't think that just because 10 is a small number, it's 10 to the minus 10, these powers that we're talking about. That's an incredibly small distance, and atoms are very, very small indeed. Excuse me. Okay, like I said, if at any point you want to ask me any questions, just unmute yourself and leap in. But if you don't do so, I'm just going to push on. Okay, I'm not going to recap with you the experiment that Rutherford did. It's on page 470 of the textbook. And if you don't remember it, please have a read of it. What I do want to do is take you on beyond GCSE and just have a little discussion about how that experiment was analyzed. So if you imagine that that's a single gold nucleus on the right of the slide, and on the left of the slide are the alpha particles coming in. So what you need to appreciate at an A level that you didn't at GCSE is that it isn't actually possible to send a single alpha particle in and track it and watch where it goes. Radioactive sources emit thousands of alpha particles every second. And so thousands of alpha particles head towards the nucleus. Also, they're not all going to be traveling in exactly the same direction. So I've drawn some alpha particles in this picture that are all traveling parallel left to right. But for every set of 5 alpha particles that are traveling like that, there'll be thousands of others that are traveling in other directions. Also, it's not possible to line an alpha particle up or know if an alpha particle is lined up with the nucleus. So every alpha particle that sets off towards the nucleus, you don't actually the nucleus it is. So there's this variable B, which is the kind of distance between horizontal lines between the actual path of the alpha particle and a head-on collision path of the alpha particle, between that red dashed line and each of the blue lines. Now, we have no idea what B is for any particular alpha particle, but it does make a difference. When you run the calculations and you apply the repulsive force from the nucleus, which we haven't studied yet, but we will, and you have to do some two-dimensional integration in polar coordinates here, which is a little bit beyond the A level, which is why we're not going to do the calculations. But you can relate B to the angle of scatter. And then you need to apply a statistical model using a kind of probability distribution from mathematics, from statistics, and you apply your probability function to B, and you get a range of likely scattered angles. So like 10% might have scattered through 13 degrees and 20% might have scattered through 18 degrees. And all of those values come from the statistical spread of the values of B and the diameter of the nucleus. So what you do is you end up with a set of statistical probabilities that depend on the size of the nucleus. And then you do the experiment and you record what the percentages are that scatter through 10 degrees and 20 degrees and 30 degrees. And then you try to match your observed set of percentages to the model's predicted set of percentages. It's incredibly complicated, and it's what led to Rutherford, or in large part what led to Rutherford getting his Nobel Prize. It's a really, really complicated calculation that these days PhD students would study for about 6 months before they fully understand it. So we're not going to go into any more detail than that, except to suggest to you that it is possible to get a feel for roughly how big a nucleus is. It's a kind of fuzzy zone, so we're not going to get an exact value for it, but it does come out at around about 10 to the minus 15 of a meter. And that's another 10,000 times smaller than the atom again. So if you imagine that very, very tiny atom that we just spoke about, 1 million of them across a human hair, actually 10,000 times smaller than that is the nucleus. 10 to the minus 15 is a femtometer, by the way, with a lowercase f. Okay, so let's try and put that into context. How big is 10 to the minus 15? Well, I'm not entirely sure this is possible to get our head around it, but to give an idea, you know how fast light travels, 300,000 kilometers every single second. It can get around the Earth 10 times in a single second, and it can travel 10 to the 16 meters in a year. So we're talking about you being a small compared to how far light can travel in an entire month, which is a vast distance. Or if you do want to treat the 10 to the minus 15, your body occupies a volume of approximately 60 liters-ish. And so if we were to disappear all of that empty space out of your atoms, we could get your volume down so small that you'd fit into about 6 times 10 to the minus 10. And given how many people there are on this planet, if we could vanish away the empty space, we could fit the entire human race roughly inside a dice or a sugar cube. So 10 to the minus 15 is incredibly small. In fact, Richard Feynman, a famous physicist from the last century, he famously had this phrase, "There's plenty of room at the bottom," and he invented the entire science of nanotechnology by suggesting that, you know, we shouldn't take for granted that the size of 1 meter is an appropriate size. Atoms are 10 to the minus 10 times smaller than us, and if we could just make smaller machines, I mean, there's as much room below us going down to 10 to the minus 10 of a meter as there is above us going all the way out to the size of Pluto. So Feynman was fully supportive of the idea of making lots of smaller devices instead of bigger devices and taking advantage of all this room at the bottom. Okay, any questions so far? Because we're going to skip on to more subatomic stuff. Any questions about alpha particle scattering? Okay, on we go then. Okay, the word nucleon is probably a new word for you. Might not have heard that before. It's the word that nuclear physicists use when they don't really care whether they're talking about protons or neutrons. So welcome to that word. Feel free to use it. So for instance, there are 12 nucleons in the nucleus of a carbon-12 nucleus. You would instead have had to have said there are 6 protons and 6 neutrons before. But if all we're talking about is size, and we don't really care if it's a positively charged proton or a neutron, if all we care about is size, you can just use the word nucleon. Okay, so how have we gone on? Rutherford was working in about 1910. How have we gone on in the last century? Well, we've come on a long way. It's now possible with the kind of machines that exist in particle physics laboratories like the ones at CERN. You can actually now accelerate neutrons up to high speeds, and because the neutrons are neutral, they don't get repelled as easily by the nucleus, and so they can get much closer to the nucleus before interacting with individual nucleons in a way that we'll talk about on Wednesday. And you can actually scatter individual neutrons off individual nucleons. In another Nobel Prize winning piece of physics, it's exceptional. And it turns out that an individual nucleon within the nucleus has a radius of just under a femtometer. So remember, the nucleus was coming in at a few femtometers. The radius of a single nucleon is coming in at about 0.85 of a femtometer. Now, that isn't a number that you need to remember, because actually the nucleons, for reasons that we will come on to on Wednesday, they don't actually touch. They're very, 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 very close together, but they don't actually touch. And so what's more important to us is not so much how big they are, but how much space they take up within the nucleus. And it turns out that the radius of a single nucleon is around about, or the radius of the space that a single nucleon occupies is around about 1.2 times 10 to the minus 15 meters. And again, that's a number that it would be helpful if you could remember. So definitely the 10 to the minus 15 meters-ness, but if you can remember the 1.2 as well, that would be really helpful for calculations that will be coming up in the future. The grey bit at the bottom just quantifies the word approximately a little bit. You'd think that if we're doing an experiment this good and we've got a value of 0.85, that sounds pretty accurate. Why have I got the word approximately in there? Well, just as a heads up for what's coming along in a few lessons' time, it turns out that actually, much to our surprise, nucleons aren't actually spherical. So a proton isn't actually spherically shaped, and neither is a neutron. So I've said an approximate radius because spheres have a radius, but non-spherical things don't. So this is the kind of radius it would have if it was a piece of plasticine and we remolded it into a spherical shape. But they aren't spherical shapes. They're slightly triangularly shaped. And we'll come back to that in a future lesson. Okay, that was all about size. So the key factors to remember from size, 10 to the minus 10 of a meter for a atom and 10 to the minus 15 of a meter for a nucleus. And if you can remember 1.2 times 10 to the minus 15 of a meter for a nucleon, that would be great. Unmute yourselves now if you want to ask me any questions. Okay. Let's push on to how heavy things are. What is the mass? Okay, so first thing to say is that mass is a subatomic property of the individual constituent particles that make up objects. What is mass, you're probably aware, is a big question in physics. CERN are investigating all kinds of clever ideas involving words like Higgs boson and things like that. And we will come back to the question of what is mass. But for now, we're going to take a much more pragmatic understanding of it. And it's the figure that comes up when you put stuff on a top-pound balance. How much stuff something is made of. And we'll come back to a better definition later. Okay, so let's ease ourselves into the mass of atoms by reminding ourselves some things from chemistry. So you know that on a periodic table is printed the atomic number, which is how many protons there are, and then there's a relative atomic mass as well. So you know that hydrogen has a relative atomic mass of 1, helium has a relative atomic mass of 4, and the chemists even refer to the relative atomic mass as the mass number, whereas in physics we recognize it for what it is, and it's the number of nucleons. So when we say that helium has a relative atomic mass of 4, what we really mean is that a nucleus of helium has got 4 nucleons in it. And how are we getting away with this? It's because protons and neutrons pretty much have the same mass as each other. Note that they are not identical, and we will come back to that because that is going to be very important. At GCSE, and in chemistry, actually, we kind of just take this approach that protons and neutrons do have exactly the same mass as each other, but they are subtly different. We'll come back to that in a minute. And each of those masses is around about 2,000 times larger than the mass of the electrons. So when you're piling up a pile of copper on a top-pound balance and working out its mass, if you're only going to measure the mass as 63.5 grams, and you're going to stop at half a gram, there's not really any necessity to pay attention to the electrons because any mass difference there is going to come out in the 3rd or 4th decimal place. And there's not really any reason to pay attention to the difference in masses between the neutrons and the protons, because as we'll see, they're down in the 6th decimal place. So in terms of a GCSE approach or a chemistry approach where you are literally weighing things on a balance, it is completely fine to just count nucleons. So helium-4 relative atomic mass of 4 means that there are 4 nucleons. However, we do need to ask ourselves, what are we making our relative mass relative to? Okay, before we get to that, just a little aside for any of you that are chemists. When the chemists are putting elements onto their balances to measure them, there is a small problem in that there are lots of different isotopes. So you might put, I don't know, chlorine on a balance in a jar, and you might sometimes find that the mass is, oh, I've given the example of copper there, isn't it? It's in front of me, so I'll use that one. You might find that sometimes the relative atomic mass would be 63 and sometimes it's 64. But if you're a chemist, you can't tell the difference between copper 63 and copper 64 because chemically they're both copper and they both behave like copper and they do all the reactions of copper. And when you do any of your purifying techniques to establish that you have a pure sample of copper, you will have copper, but it's not going to be a pure isotope of copper. You're going to have a mixture of copper 63 and copper 64. And the abundance of each isotope in your sample will match pretty much the abundance of copper on Earth. And it turns out that around 2/3 of the copper on Earth is copper 63, but the other third of the copper on Earth is 64. So when you are suggesting what the relative atomic mass of copper is, should you say it's 63 or should you say it's 64? Well, really what you need to do is blur the two together a little bit. 2/3 63 and 1/3 64, and take a mean of those numbers. So when you do that, you will find that you end up with a decimal value for your relative atomic mass, which is no longer a relative atomic mass if you're going to think of relative atomic masses as the number of nucleons. So we call this a standard atomic mass, except the chemists aren't playing by the rules, and they've decided to call it a standard atomic weight, which makes me grumble because it's not a weight, it's a mass. So really a standard atomic mass, but you'll see it referred to as a standard atomic weight. This is taking into account the abundance on Earth of the different isotopes. So if you are a GCSE chemist, you want to be thinking about relative atomic masses. But if you are an A-level chemist or above, you probably want to be thinking about standard atomic weights when you're doing your mole calculations and things like that. Anyway, that's just a little aside for the chemists. If you're a physicist and not a chemist, you don't need to worry about that slide. Okay, so relative atomic mass relative to what? Well, it's relative to the hydrogen atom, isn't it? The hydrogen atom has a mass of 1 because it has 1 nucleon. So if we could just mass 1 hydrogen atom, this would be great. Unfortunately, we can't. In order to mass a single atom, we would need much better measuring devices than we have. So practically, in order to find out the mass of a single atom, we need to do a similar calculation to the one that we did at the start of this lesson. And we need to mass a macroscopic amount of something that actually shows up as a few grams on the top pound balance. And then we need to divide by how many atoms we've got in that sample. Well, if we're going to do that, then the sample that we place on the top pound balance needs to be a pure single isotope. And hydrogen, just like most other elements on the periodic table, is not a pure single isotope on Earth. There's hydrogen 1, hydrogen 2, and hydrogen 3 with no neutrons, 1 neutron, and 2 neutrons. And so if you were to go and get yourself a sample of hydrogen, it wouldn't be a pure isotope. So the chemists, they scoured around for a long time. They looked at all of the different samples of all of the different elements on Earth, and they discovered to their glee that carbon on Earth is almost pure. It's something like 99.999999% pure, which means that if you do put a pile of carbon on a top pound balance, you can be pretty certain that actually practically every atom in that sample is carbon-12. And so what we have decided to take is that the mass of 1 nucleon we're going to take to be 1/12 the mass of a single atom of carbon-12. So what the chemists do, they go get a whole load of carbon-12, they put it on a top pound balance, they take the mass of the whole load of carbon-12, and then they divide by how many atoms are in their sample using Avogadro's numbers and moles, like we did at the start of the lesson. And then whatever the value they get for 1 atom of carbon-12, they then divide that by 12 to get the mass of a single nucleon. So this is referred to by the letter U and the name atomic mass unit. And you'll note by the number of decimal places there just how precise these measurements have been made. So the mass of a single nucleon, 1 proton or 1 neutron, is 1.660539,040 times 10 to the minus 27 of a kilogram. Now, that is not a number that you need to remember because it's on your data sheet and it'll always be given to you in any questions or exams. But you should have a feel for that 10 to the minus 27. You should try to fix that number in your head that a single nucleon has a mass of 10 to the minus 27 of a kilogram. Okay, that's an atomic mass unit. Just like we sometimes use electron volts instead of joules because it's a much more appropriate number, we are very regularly going to be using atomic mass units instead of kilograms during this topic. So you need to be comfortable flicking between the two units in the same way that you've become comfortable flicking between electron volts and joules. Okay, so that's a number you need to fix as useful in your heads, 10 to the minus 27. The reason we don't ask you to memorize it is because you will regularly require all of those decimal places when you're doing calculations. You can't round these things off because the numbers are so small, the differences. Okay, so having established the atomic mass unit, we can now talk about absolute atomic masses rather than relative atomic masses. And by making our choice of unit to match the mass of the nucleon, actually to flick between relative atomic masses and absolute atomic masses, people don't use the word absolute, they just say atomic mass. So to flick between relative atomic mass and atomic mass, all you need to do is write a U on the end of your number. So the relative atomic mass of helium-4 is 4, and the atomic mass of helium-4 is 4U. Now, if you're a chemist, you would stop there, and that's utterly fine for nearly everything you would study inside chemistry. However, as physicists, you need to understand that the atomic mass of helium-4 isn't 4U. And that's for the following 3 reasons, and you do need to understand what these 3 reasons are. So, reason number 1, protons and neutrons don't actually have a mass of 1U. They are very, 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 very slightly different from 1U for reasons that we will come on to. But inside the carbon-12 measurement, the slightly heavier neutrons and the slightly lighter protons have obviously been averaged out a little bit to arrive at the value of 1U. We're also ignoring the mass of the electrons. I said that the mass of the electrons was a 2,000th. It's an 1800th of the mass of a proton and a neutron. But when we're dealing with all of those decimal places, the mass of the electron is coming in around about where the 5 is. And so actually, if we do want to be exact, we do need to take into account the mass of the electrons. So the chemists aren't going to go down as far as the 4th decimal place, but the physicists are. So we do need to pay attention to the mass of the electrons. And finally, there is a quantity that you haven't met yet that we're going to do in a lesson very soon next week called binding energy. And whatever that cool sounding stuff is, this binding energy inside a nucleus, it does affect the masses that we measure. And so by neglecting it, we do make an incorrect measurement. So to recap, it's okay if you're only dealing with 1,000th of a gram or so to take the atomic masses as just scaling up by a factor of U. But in physics, where we're going to be down at the 6th, 7th, 8th, 9th decimal place, that's not accurate enough. And we are going to have to take into account the electrons, the difference in masses between the protons and the neutrons, and also this thing called binding energy. Okay, I told you at the beginning that we would have a little reminder about moles and Avogadro's number. So I'm not going to reteach you moles. I know that if you are doing A-level chemistry, you are retaught moles and it takes a few lessons. I'm not going to do that. As physics students, you don't need a rigorous definition of moles or Avogadro's constant, but you do need to know what they are. So this is what you need to know as a physics student. And if you want to know more, the Wikipedia articles on both moles and Avogadro's constants are actually pretty good. Some Wikipedia articles are a bit ropey, but the 2 for these are fine. So you can have a little read if you want to. Or if you are a chemistry Student, you've either done this already or you will be doing it. Okay, so what is a mole? A mole is one of the 7 or 8 base units, and this is the unit for amount of stuff, but we could hardly write that on the definition of an SI unit, so we use the word substance instead. So the mole is the SI unit for amount of substance. So it's up there along with the meter and the kilogram and the second and the amp. It's got its place at the top table. It's a fundamental unit of science. So give it the status it deserves. And it is literally a count. You count up your objects, and if you have a certain number of them, we say you have 1 mole. So how have the chemists chosen to define it? Well, they're sticking with their carbon-12, and what they're saying is that 1 mole of a substance is however many particles there are, however many atoms there are in 12 grams of carbon-12. So I wouldn't want you to think that somebody sat there with 12 grams of carbon-12 on their top pound balance and then sorted through it with a microscope and counted the individual atoms. The chemists have much cleverer ways of doing things than that. Like I said, read the Wikipedia article to find out actually how we justify what a mole is. But if you are ever doing calculations in moles, the thing from this slide that you need to pay attention to is that moles refer to 12 grams of carbon-12. Moles are always in reference to grams. And if you start switching to kilograms while you're doing your calculation, you're going to be out by a factor of 1,000 in your answer. So when you do some questions, that will be much clearer what I mean with that bear trap, not to fall into it. But just remember, it's 12 grams, not 12 kilograms. And in defense of the chemists, we only made the kilogram the SI unit about 40 years ago. Prior to that, the gram was the SI unit. So when we updated the SI table to include kilograms instead of grams, I guess the mole just didn't update its value to take into account kilograms instead of grams. Okay, it is possible to put a number to how many atoms there are in 12 grams of carbon-12, and that number was first measured about 100 years ago by someone called Jean Perrin. But Perrin had been working on a hunch from something he'd read from something that had been written 100 years before that by an Italian guy called Avogadro. So when Perrin established the value for the number of particles in a mole, he wanted to bring a claim to Avogadro and have history remember Avogadro. So in quite a nice moment in history, Perrin named the constant after Avogadro. So it's always referred to as Avogadro's constant now. Capital N with a subscript of a capital A. And that value of 6 times 10 to the 23, again, is a number that will appear on your data sheets and be given to you in exam questions, but is not a number that you need to memorize. But you should have a feeling for the 6 times 10 to the 23-ness. Certainly, if you're a chemist, you should definitely try to fix that number in your head. Okay, you'll note how accurate that number is. Again, if you're interested in how we manage to measure something to that level of precision, read the Wikipedia article about it. But it is one of the greatest triumphs of chemistry to measure that number, one of their proudest moments, and it is worth a read. In fact, it's such a good measurement that there are still arguments going on today to redefine the kilogram in terms of Avogadro's constant. So if you go to the National Physical Laboratory, NPL, go to their website, they'll show you a video all about how we define the kilograms and arguments for and against using Avogadro's constant in that definition. Okay, so we've got enough time to move on to density. We now have the radius of a single nucleon. It's 1.2 times 10 to the minus 15 of a meter. And we have got the mass of a single nucleon is 1.66 times 10 to the minus 27. Given that the 1.2 is a 2 sig fig number, it doesn't really make sense to keep 8 significant figures for the U. So why don't you just try on your calculator quickly now, using the formula for the volume of a sphere as 4/3 pi r cubed. Just tap those numbers into your calculator and just check I haven't made a mistake. You do need to be able to calculate the density of a nucleon. So mass divided by volume. Try it on your calculator now. I'll just be quiet for a second. You get stuck and want to ask any questions, just unmute your microphone and ask them. Okay, so you should have tapped into your calculator. 1.66 times 10 to the minus 27 on the top, and you need to divide that by 4/3 times pi times that radius cubed, 1.2 times 10 to the minus 15 cubed. If you have got the answer wrong, just check the algebra on your calculator screen. Make sure that you're cubing the 1.2 as well as the 10 to the minus 15. Make sure that you've entered the 4/3 pi properly on the bottom of your fraction. Okay, so 10 to the 17 kilograms per meter cubed. So think about a meter cubed. It's kind of, I don't know, 2 shopping trolleys parked side by side. Half of your kitchen table, something like that. A meter cubed isn't that big. And then think about 10 to the 17 kilograms being squashed inside that meter cubed. What does 10 to the 17 kilograms even look like? What does have a mass of 10 to the 17 kilograms, be it a meter cubed or not? Well, it turns out from calculations that geophysicists have done that the entirety of Mount Everest has a mass of around about 10 to the 14 kilograms. It's an estimated mass because obviously you have to ask yourself, where does a mountain stop? Is it at ground level or do you carry it down on into the crust? I think that estimate finishes at ground level. So the amount of Mount Everest above sea level, maybe. So, well, not sea level, it must just be ground level. It's an approximate. So what we're saying is that you could fit 1,000 Mount Everests inside 1 meter cubed. And if you did that, that would be the density of nuclear matter, 1,000 mountains in a single meter cubed. Or to put it another way, 1,000th of a meter cubed would have the same mass of the entire mountain. So 1,000th of a meter cubed is around about a standard bucket, one of those orange B&Q 53p buckets. So if you were to pour nuclear matter into a standard bucket, it would have the mass of an entire mountain. So nuclear matter is pretty dense, and it is actually realized. It's real stuff. It exists in the universe, and you'll study it next year when you do the astrophysics unit with Mr. Downing. There are types of stellar objects called neutron stars. And neutron stars are exactly what you think they are. They're stars made of pure solid neutrons. And they do have a density of 10 to the 17 kilograms per meter cubed. These are real objects that really do exist in the universe. So more on that next year. Okay, last slide for today. I think we've done enough and we'll call it a day at the end of this one. So just to note that the density of all nuclei is the same as the density of a single nucleon. And the reason for this is that there isn't really any space inside a nucleus. I said that the nucleons themselves don't actually touch, but we have taken the radius of a nucleon to be the zone they occupy. And therefore, we've kind of included in our calculations any hollowness to the nucleus. So this is a calculation that sometimes you're expected to demonstrate in an exam. What we say, if we just look at the one at the bottom of the screen first, we've got the density of a nucleus is the mass of the nucleus divided by the volume of the nucleus. But actually, the mass of the nucleus is just the mass of a single nucleon multiplied by how many nucleons there are. And the volume of the nucleus is just the volume of a single nucleon multiplied by how many nucleons there are, if we accept that there's no empty space inside the nucleus. And therefore, in that calculation, the two A's cancel out, and we're left with the density of any nucleus is the same as the density of a single nucleon. It seems silly to have to put algebra to it when we just say the words, there's no empty space. But that calculation could get you some marks in an exam one day. So note how to write it down. And then sometimes we're asked to talk about the size of different nuclei. So how would a big nucleus compared to hydrogen in terms of meters? So this comes down to volume calculations now. So if you look at the top line of algebra now, we've got the radius of a nucleus is r, and therefore the volume of a nucleus is 4/3 pi r cubed. But if we're going to say that the volume of the nucleus is just the volume of a single nucleon multiplied by how many nucleons there are, we always use the capital letter A for the number of nucleons, the mass number. We end up being able to write that equation, and then we can cancel out the 4/3 pi and take a cube root of both sides of the equation. And we find out that the radius of the nucleus is proportional to the radius of a single nucleon. And this constant of proportionality is the cube root of the number of nucleons. So to give you an example that easily we can cube root in our head, aluminium-27 is an isotope of aluminium. It has 27 nucleons in its nucleus. So how big is a nucleus of aluminium-27 compared to a nucleus of just one nucleon, so hydrogen, and we need to cube root the 27. So the cube root of 27 is 3. So we would expect that if we placed a nucleus of aluminium-27 next to a single nucleon, then the aluminium-27 nucleus would have a radius about 3 times bigger than the single nucleon.